All right, so this is 11.3, day 1, continuity and an introduction to limits. So we are starting chapter 11, and our objectives for today, we're going to be able to determine if a function is continuous at a point and be able to understand how to find the limit of a function graphically. So I know we've talked about continuity in chapter 2, so let's just review. Graphically speaking, a function is continuous at a point if the graph does not come apart at that point. And we can think about, we can illustrate that concept with a few graphs. So if you take a look at this first graph, notice that it's continuous at all x, because for x values close to any particular real number a for the function f, we are assured that the f of x values will be close to f of a. Notice there are no breaks in that graph. Part B, this graph is continuous everywhere except at x equals a. So for x values close to any particular real number a for the function f, we are not assured that the f of x values will be close to f of a. In this case, f of x is smaller than f of a for x values near a. So again, all of these x values near a, notice our output values are smaller than f of a. F of a is way up here. So notice this is called a removable discontinuity because it can be patched by redefining f of a so as to plug that hole at x equals a. So this is not continuous at x equals a. Part C, this graph also has a removable discontinuity at x equals a because for x values close to any particular real number a for the function, we're again not assured that f of x values will be close to f of a. In this case, f of a does not even exist. It is removable because redefining f of a could plug that hole and make f continuous at x equals a. Now for part D, this is actually a jump discontinuity. So for part D, we call that a jump discontinuity. It is not removable because there is more than just a hole at x equals a. There's no way to redefine f of a to plug the gap with a single point a comma f of a. There's a jump discontinuity at x equals a. If you take a look at E, this is a function with an infinite discontinuity at x equals a. So again, not continuous at x equals a. Let's take a look at some more examples on the next page. So if you notice, let's see our statement here. It says a function continuous at x equals a if it is not continuous at a. So a function is continuous at x equals a if the limit of the function as x approaches a is equal to f of a. So we need to talk about limits. And we had an introduction in earlier in the year. But again, let's talk more about limits. Here's our informal definition. If we write limit of the function as x, limit of the function as x approaches a equals L, that means that if as f of x gets f of x gets arbitrarily close to L as x gets arbitrarily close but not equal to a. So as our input, our x value gets arbitrarily close to a, our f of x gets arbitrarily close to L. And again, L must be a fine number. Okay, so if you take a look at number 2, this is saying at a limit. So I want to know what is the limit of the function 1 over x as x approaches infinity. So if we calculate 1/2, 0.3, 1/10, 1 over 100, 1 over 1,000, 1 over 10,000, notice that those values are getting smaller, smaller, smaller. So graphically, as x approaches infinity, 1 over x value approaches 0. Okay, so let's talk about left and right-handed limits here. So if we have the limit of the function as x, notice that negative sign is telling us from the left. And the limit of the function as x approaches c, that positive sign is telling us from the right. So a function f of x has a limit as x approaches c, if and only if the left and the right-hand limits exist at c and are equal. So let's do number 3. Notice that says, what is the domain of f of x? We have already our domain. And if I wanted to find the limit of the function as x approaches infinity, let's think about what we learned in chapter 2 when we talked about rational functions. And talked about how, for example, for this rational function, for a very large or very small x values, the 2 and the 1, they're kind of they become kind of insignificant, and you will have a horizontal asymptote at y equals 1. So that's why we have, as x approaches infinity, our y, our f of x, our output is approaching 1, and as x approaches negative infinity, our output, our y, our f of x, is approaching 1. So if I say to you, what about the limit of the function as x approaches 0 from the right? Notice as x is getting closer and closer to 0 from the right, our y value, our f of x, is 2. As x approaches 0 from the left, our y value is 2. So the limit of the function as x approaches 0 does exist because the right and the left-hand limits both exist, and they are both 2. So our limit of the function as x approaches 0 is 2. So is the function continuous at x equals 0? Yes, because the limit of the function as x approaches 2 from the right, as x approaches 0 from the right, the limit of the function as x approaches 0 from the left, they are both equal to 2, and f of 0 is 2. So yes, the function is continuous at x equals 0. Go ahead and try problem number 4. Pause the video and see how that goes. Okay, so for number 4, we have x squared minus 1. And what is the domain? The domain is all real numbers. Now, b and c might be confusing because when we talked up here, we talked about how the limit of a function as x approaches c, that L must be a finite real number. And so if I say as x approaches infinity and negative infinity, notice how I said that the limit was infinity. So technically, a limit has to be a finite real number, and infinity is not a finite number. So technically, the limits don't exist, but it's convenient to write infinity because then you think about why it doesn't exist, and it helps you to kind of visualize what's going on. So that's why we write infinity there. But again, technically, it must be the limit of a function must be a finite real number. So for part D, looking at the graph, you might say, well, it's kind of hard to see. 5 is way over here. So do you see how we kind of could substitute 5 in for x to see that, oh, the y value is 24. So as x approaches 5 from the right and the left, those limits both exist and they're equal. They're both 24. So the limit of the function as x approaches 5 exists, and it's 24. And that's why f of x is continuous at x equals 5, because the right and the left-hand limits exist, and they're the same, and f of 5 is that same value of 24. Go ahead and try 5a, b, and c, and see how that goes. Pause the video, please. All right, so here we are for number 5a. And number 5a, notice we have a removable discontinuity right here at 3, 4. So if I say to you, what is the limit of the function as x approaches 3 from the right? So as x approaches getting closer and closer, arbitrarily close to 3 from the right, the y value is approaching 4, the output. So the input as the input from the right, the output value is approaching 4. As the x approaches positive 3 from the left-hand side, notice that the f of x is approaching 4. So since the right and the left-hand limits both exist and they're equal, the limit of the function as x approaches 3 is 4, and it does exist. So if I ask you, is f of x continuous at x equals 3? The answer is no, because even though the limit of the function as x approaches 3 exists, f of 3 is not 4. F of 3 does not even exist for number 5a. Take a look at b. So for b, I want to know what is the limit of the function as x approaches 3 from the right. Notice there isn't even anything there. So that limit does not exist. Now, the limit as x approaches 3 from the left, that limit actually does exist, and it's 4. So the left-hand limit does exist, and it's 4. The right-hand limit does not exist, so the limit of the function as 3 does not exist, and that's why, no, it is not continuous at x equals 3. f of x is not continuous at x equals 3 because the limit of the function as x approaches 3 does not exist. Lastly, part C, notice that they're asking you about the limit of the function as x approaches negative 3. Now, as x approaches negative 3 from the right-hand side, the y value, the output, the f of x, is approaching 2. But notice there is nothing left. So if I say the limit of the function as x approaches negative 3 from the left, that limit does not exist. So in order for a limit to exist, The right-hand limit has to exist, the left-hand limit has to exist, and they have to be equal. So that's why the limit of the function as x approaches -3 does not exist. And f of x is not continuous at x equals -3 because in order to be continuous at a point, the function, the right-hand limit has to exist, the left-hand limit has to exist, and they have to be the same value, and that value has to be the same as f of that value. So notice this is definitely not continuous. Actually, let me start again. So as x approaches, if I want to know if it's continuous at 3, the right-hand limit as x approaches 3 and the left-hand limit as x approaches, start again. Sorry, I think I might have confused you. So in order for a limit to exist, the right and the left-hand limits must both exist and be the same. As far as continuous goes, the function is continuous at x equals -3 only if the right-hand limit as x approaches -3 and the left-hand limit as x approaches -3 are the same, and also that f of -3 would be that same number, which is not the case here. So f of x is not continuous. So f of x is not continuous at x equals -3.